Let's do an example of a problem, how we get to average velocities. So if the average velocity is the average velocity is defined as the displacement over the change in time it took to make that displacement. Or, we know displacement equals x2 minus x1, and the time you finished at is t2. Subtract that from the time you started at, t1, we can calculate an average velocity. Let's do an example. Let's say you are starting out at home. And for the sake of convenience, home is always your origin. So we'll call the position of home 0 kilometers. And you need to drive to the Kennedy Expressway and take the Kennedy out to O'Hare. So you drive to the Kennedy, and once you get on the Kennedy, you drive to O'Hare Airport because you're going on vacation. And it turns out the Kennedy is about 3 kilometers from your house. And O'Hare is 13 kilometers from your house. So, let's say you leave home at 12 o'clock. And you get to the Kennedy at 12:05. Or let's make it 12:06. And then you finally get to O'Hare at 12:12. So overall, it took you 12 minutes to get to the airport. You drove to the Kennedy, got on the Kennedy, and then went to the airport. Now we can calculate the average velocity for each of these. So we'll call this average velocity v1. We'll call this average velocity v2. So the average velocity it took you, that you used to get from home to the Kennedy, was delta x over delta t, which equals where we ended up, which is 3 kilometers, minus where we started, 0 kilometers, and it took 6 minutes or 1/10 of an hour to do that. So 0.1 hour minus 0 hours. So 6 minutes is 1/10 of an hour. We started at 0 because that's convenient, and it turns out that our average velocity was 30 kilometers per hour. Now we can do the same thing with v2. However, our numbers are a little bit different. We ended up at x2 minus x1 over t2 minus t1. We ended up at 13 kilometers away, and we started 3 kilometers away. And we got here after 2/10 of an hour, and we're starting at 1/10. Which then gives us an average velocity of 10 over 0.2 is, I guess I got to calculate that. Oh, I don't have my calculator. Well, anyway, it is 100 kilometers an hour. So 100, so this equals 30, and this equals 100 per hour. Now let's say you got to the Kennedy and you forgot something and you had to go back home. Well, that means you would have to go the other way. Remembering that this is still 0, and this is still 3 kilometers. Now let's say you traveled the same speed, and so it was 12:06 when you got to the Kennedy and decided to turn around, and by the time you got home, it was 12:12. We'll call this V3. V3 equals delta x over delta t. So now we put in the x we ended up at, which in this time is 0 kilometers, minus the one we started at, which is 3 kilometers. Now time always moves forward, so the time we end up there is 0.2 hours, and the time we left at was 0.1 hours. Now if we do the math here, we get negative 30 kilometers per hour. Now notice, the magnitude is exactly the same, but the direction is different, because 0 is the home where we started at. Now normally, we make 0 where we start at any time, but we're talking about a round trip. We, going back the way we came, is usually negative. So going east is in the positive direction, going west is in the negative direction. Hey, let's say we did the whole thing going round trip. So round trip, we started at, we'll call this VRT equals x2 minus x1 over t2 minus t1. In this case, x2 is where we started at. Is where we ended up, which is at home. So it's going to be 0 kilometers. x1 is where we started at, which was home, which is also at 0 kilometers. And over that time, it took us 0.2 hours. What's that equal? Well, that equals 0 kilometers per hour. So it doesn't matter if you go out and come back. If you always end up in the same place, you have no velocity. So that's how these things work with directions. If we take a really quick look and maybe consider our path. The thing about our path is that we started out here at home at 12 o'clock, and as we're driving to the Kennedy, when we got there at 12:06, we went, 1 kilometer, 2 kilometers, or 3 kilometers. We probably pulled away from our house, stopped at the corner, got in Irving Park, drove pretty fast, had to stop for another light for a little while, then got stuck in traffic, so we went really, really slowly, and then stopped at another light, and then we'd go really, really fast until we got to where we were going. Now, if we look at this plot of our position versus time, we see that it's not straight. However, when we make our calculation here at 0.1 hours and 3 kilometers after we started from 0, 0, our average velocity goes from, here on the straight edge, another color, is calculated based on the straight line distance. Now you can see here that when we take velocity equals delta x over delta t, we see t is on the y-axis, t is on the x-axis, the change in displacement is on the y-axis, So this is just like calculating a slope. So the higher your average velocity, the steeper your slope becomes. And we can see that on our trip, we were moving at different velocities. So this is our average velocity from place to place. And next time, we're going to talk about the instantaneous velocity. So we call this delta x, this here is delta y, and we can compute velocity as the slope. So this is the average velocity with respect to displacement equals delta x over delta t.